Hello, welcome to ClojureRank, solving this hackerRank problem here. This is a bit of an algorithm problem where we're searching through a 2D array and we're counting islands. Now, islands in this case are the ones in this 2D array. We can see it laid out. If you know what an array is, it's each of these rows is an array, and overall we have an array of arrays. And we are meant to find the islands and count how many of them there are. So apparently here, the input format is the number of rows, number of columns, followed by the matrix, print the number of islands. Output should be 5, so that means there's 5 islands, and those would be this one here, this one on the right-hand side, and then these 3 individual dots on the bottom. Got us a little archipelago. And we're going to count these. I'm a big fan of archipelagos myself. Got some great archipelagos out there. And this one we're going to count how many islands are in it. I'm going to do it in Clojure as usual. And I've gone ahead and added some just some little input-output code to start with. But yeah, so let's get to it. Overall, the approach is going to be one of depth first search. So enumerating through each row and each column, when you come to a 1, we're going to treat the island like a tree, and the root is wherever we happen to start on that island. The children are the adjacent squares of the island, and we're going to search through them until we've found every square in the island. And then we remove that island from the board and count it, because the only thing we have to do here is count the island. Normally in depth first search, you're searching for a particular node, but it can also be used to simply enumerate all the nodes in a given tree. Right. Got a little celebrity guest here as well. Bosco, come here, Bosco. Say hi. He's tired. He had a long day. There was a cat in the yard. So. Good boy. All right. Overall, just count islands. And so what we're going to do is iterate each row and column. Yep. Yeah. What do you think is happening? I equal rows would mean that we've already gone over the row where I equals count minus 1, and now we've incremented it again, so we're done. We've done every row. Okay, so the next case we're gonna either find an island at the given location or we're not. Matrix should be a vector, so we can get in. Okay, so we found an island. Now we're gonna recur with new I, new j, and I'll get to those just a second because there's a little bit of math there. We'll write this momentarily. Yep, and then the other case, same iteration logic, but instead we just pass in the node. In the island count. I think that's it, yep. To achieve this iteration, I don't know why I'm doing it like this. There's obviously many ways to increment I and j as you go through, but this is what's working in my head right now, so I'm gonna do it. Now I would be and j is going to be always incremented, but mod yeah, let's put this in a little function because I'm about to use it twice. Cool, so now we have to write the next thing down the stack, which is remove island. And that's the depth first search part. So let's say, call it matrix again, why not? Okay, so yeah, so the algorithm here, we have a starting point. We're going to assume that the starting point is a 1 because we're going in there because we found an island. That's the only time this is going to be called. And now, yeah, now the thing to do is to create a stack. I think it can just be a loop right off the bat. Well, because we still want this column and row logic. We're knowing the stack. So the depth first search algorithm is you have your node, you have the root node, and you push the children of the root node. In this case, we're calling them neighbors, but they're more like children. And you push them on the stack. Then you loop around, and you process the node you visited. You put, that could be the root, it could be the next one. You put the neighbors on the stack, and then you mark the current node visited, and then you recur and pop the next one off the stack. Eventually, this process of marking the nodes as visited and pushing the unvisited onto the stack leads you down each trajectory in the tree as far as you can go, and then you recur back up and finish the algorithm. Right, so we got a stack, and we're going to get the neighbors of that so we can put them on the stack. And the current is so that's when we've reached the end, is when we've pulled off the stack and there's nothing left on it. That's when we reach the end, and then we return the, okay, we need another variable up top because we need it in the loop. That's where we need it. Yeah, okay, so we got another variable there, and we're going to treat that, because we're gonna update it each iteration. Need update. I think you can assoc, I never know how to say that, but I think you can assoc on a vector, just like a map. Yeah, sure can. But you have to be within the bounds as far as I know. Yep. Okay, right. So yeah, this will iterate through the nodes that make up the particular island, and there's one bit that we still have to implement: get neighbors, and that is a matter of addition. So for a given I and j, what are the adjacent squares on the board? What are the adjacent nodes in the graph? And that's yeah, we need the whole nodes though, because we have to only obtain the nodes that are in the board, right? Like we don't want to add elements to the stack for -1, or for example, or even for elements that are zeros. We only want the neighbors that are on the island, because that's what we're searching. We're searching through the board to clear off all the squares of this island. How does this go? Yep, that's how it's supposed to look. And then what we'll do is add those. Oh, one more thing. This is really arbitrary, which is X and which is Y. But as long as we're consistent, because it's the same in either direction anyway. I just realized that this argument is not necessary. Yeah, so all those squares are adjacent to 4 or 5 somehow, whether up, down, left, right, or diagonal. I wasn't sure at first if it was diagonal, but the example that they gave us conveniently includes a diagonal, and it's 5 islands if you count this whole thing that's separated only by a diagonal as one island. So like if I give it 0, 0, we shouldn't see any negatives. Right. That looks right. let's try this one out, just on a simple example. So, like, what? The error is nth is not supported on this type long. So we're treating a number like a list for some reason, and probably count first. Did I get this backward? No, I didn't. What's the actual? 38. 19. Oh, right. So yeah, current is actually supposed to be that. And I'm missing something else because I'm not using the content of the matrix anywhere. What is that supposed to be? It should be so get neighbors returns a list of I and j. Are we already dealing with I and j? We're not. So here. Function of I and j. We need only those for which. Yeah, this is the remove island logic. So only those for which the square is part of the island. Well, that doesn't need to be ing either. That can just be current. Right, when that equals 1, those are part of the island, so that's where the neighbors are. Otherwise, we don't need to search the ocean. Exactly. All right, this is what it's supposed to do. What it shouldn't do is remove like every one. It shouldn't remove everyone from the square. It doesn't. And now, in this case, it should in fact remove everything because it's all the same island. Yep. Okay. All right, so that's the algorithm. That's a funny feeling sometimes. I think that's it. I wrote the thing. We'll see if it does it. Of course, it probably doesn't. Probably an error. Emacs is magic. I'm just making sure that I did this right, because inside the loop we use nodes because that's the one that gets updated every iteration. Matrix, they're both immutable, but inside the loop nodes is called with the current value, whereas matrix is immutable throughout the whole function call. What's going on here? I can read. Cool. Yep. Looking good so far. What does he do at 0? 0. Easy. Okay. Yeah, so now let me just... Cool. Yep. Okay, 5. And let's run that. Syntax error. I must have... Why is this in bash? Clojure. Duh. Like, what? I'm using string, so. Oh, right. No, this is require. Require is for Clojure namespaces. Import is for Java classes. Okay, cool. First test case worked. This one, it's only got the 3 test cases. It's from this Crescent. I don't know who the Crescent practice is or what the 3rd year level is, but they have some interesting problems on there. So I tried this one out. That's it. That's the solution. It's a depth first search with a bit of a twist. Kind of just like a weird data format that we can still treat as a tree and do a depth first search on it. So thanks for watching. Neat problem. Enjoyed solving it. Hope you enjoyed watching. Don't forget to click like on the video, subscribe so you'll be notified of new videos, and I'll be back soon. Thank you.